What section is this?
2-2. Okay. I want to start solving equations. Best part about this, you've done this before in Calc 2. I promise if you took Calc 2 here, you covered this. It's in chapter 9 in the Calc book, if you want to go back and look. It's chapter 9, section 3, I think. But the best part about this is if I have y prime equals some function of x, this is the fundamental theorem of calculus, y prime, then I know what y is. That's easy. When I do that, I get a plus c, right? And that means I have a one parameter family because I can change that value of c, and I get a one parameter family of solutions. But if I think about the normal form for a differential equation, some things are actually able to be written this way that don't look it. Here is a differential equation. I can solve this by integrating because this is really going to look like that. But I have to rearrange it to make it look right. We'll move the dx over. And then I'll divide by e to the 3x. Well, that's the same as multiplying by e to the negative 3x. Hell, I don't even have to write it y prime equals. Isn't that set up to integrate? The left side is a function of x times dx. The right side is a function of x times dx. The left side is 1 times dy. So if you integrate on the left, you just get a y. And if you integrate on the right, you get a function of x. There's my key step right there. Integrate it. And then y, I'm going to get a u sub because that negative 3x over there. So that's going to give me a what in front? I'm sorry? Because there's the 3x. When I bring that, it'll be a 1/3 to cancel out the 3. So, and then there's the negative. So the negative and the other negative is going to make this 1/3 e to the negative 3x plus c. There's my one parameter family of solutions. If I had an initial value, I would be able to plug in and solve for c. And give you an interval. But in this case, that interval is I don't have any initial value, but I do happen to know that this function is defined everywhere, right? From minus infinity to infinity. So no matter what initial value you give me, it's going to work. This line is really key. Because once I can say to myself, hey, look, everything on the left is in y and dy. And everything on the right is in x and dx. Then I can integrate with respect to dy and with respect to dx and maintain that equality. Once my equation looks like this, it's been separated. This is actually generalizable as long as the derivative thing I am looking at, the y prime, is just a function of x times a function of y. Let's take this original equation again, and let's write dy dx. I'm going to do the exact same first spot. But now I'm going to divide. Twice. And isn't that exactly what we would say? Oh, well, now I can integrate and solve for y? If I integrate and solve for y, aren't exactly in the same place I was right here. I love this fact that I can separate my variables because it means the only technique I need is to be able to integrate. That's the problem, though. I need to be able to integrate. All of the integral tricks in Calc 2, all of the formulas we learned for antiderivatives at the end of Calc 1, I need them all. If the expression for my derivative is a thing in x times a thing in y, then I am guaranteed to be able to separate. I just divide the y part over to the left and move the dx from the left to the right. And then as long as I know how to integrate on the left and I know how to integrate on the right, I'll be done. Please notice that is a big if, as long as I know how to do those integrals. So that should be an x. Is this separable? Warning, warning. I see algebra ahead. How?
E to the 3x times e to the 4y.
There's my messy algebra. When you're adding powers, you're multiplying with the same base. And now I've got a thing in y times a thing in x. So yes, that's separable. The problem is once I separate it, I'm not sure how to integrate it, but I know it's separable because I'm going to have to divide the y prime over, and I'm going to get 1 over y squared e to the minus 4y times dy equals x e to the 3x dx. Integrating on the right is integration by parts. Integration on the left should also be integration by parts, but that's 1 over y squared. Ew. I don't want to do that. It is separable, but the resulting integral sucks. Questions? With any separable equation, this is my goal. I should be able to get an explicit equation, y equals, when I'm done with this problem. So write the separated version. Um, what do I get when I separate? Let me do the easy part first. I'll separate the dy and the dx. Let's start there. And then my brain goes, wait, I need the x with the dx, and I need the y with the dy, so we'll put them on other sides. I'll have 1 over y dy, and I'll have 4 1 over x dx. Much better. Much? Well, at least it's better. It's the antiderivative of 1 over x. Of? Ta-da. What about the other side then? The only thing that bothers me about that, technically I should have absolute values in there, right? And then here I've got that 4. There's got to be at least a plus c somewhere. Technically, I could put a plus c on both sides, but then I just add them together. There we go. If all I wanted was an implicit equation for y, this is enough. But if I want an explicit y equals stuff, I can't do that at the moment. How do I get rid of that ln? Well, that is a natural log. So I need an e, right? And an e and an ln will cancel each other out when they are right next to each other. So if I do an e here, that's good. That's going to give me a y. If I do an e here, Houston, we have a problem. There's a 4 in the way. What do I do with the 4? I did warn you that messy algebra was coming. Properties of logarithms. What do I do with this number? It's out front. You did this for me on Wednesday, so I know at least you saw it before in this room. And if not, Use the internet. Look up properties of logarithms. Mia? Numbers out front come from powers inside. So I can turn this into e to the ln of x to the fourth. What happened to my absolute value? I promise I didn't get rid of it for no reason. There is a reason I can throw it away. I'm raising to an even power. So now I have absolute value of y equals e to the ln of x to the fourth plus c. Wait a minute, this addition is screwing me up. I can't cancel because of the plus. I could cancel the e and the ln, but there's that plus c that's not part of the ln. Jalen, I'm going to play your trick again. I'm going to separate these. E to the ln x to the fourth, e to the c. Wait a minute. C is just a number, right? If c is a number, then e to the c is just some other number. So now I get absolute value of y is some number times x to the fourth. There's an absolute value over there. What happens on the right if I get rid of the absolute value? You got it. And your initial condition, if you had one, would tell you what the value of A was. Now, back my ass up to the top of this. I did something that prevents this from being defined everywhere. What did I do that limits where this is defined? On the screen, guarantee it. Oh, because when you take something and raise it to the fourth power, regardless of whether it's negative or positive, you're raising it to an even power, the result's going to be positive. So I don't need the absolute value anymore. Aha! Can't take the natural log of 0. Means x can't be 0, means y can't be 0, right? Up here, I divided. I've got 1 over x, I've got 1 over y. I've thrown out any possible initial condition that has x equal to 0. Any possible initial condition that has y equal to 0. Exactly. So that tells me about the interval we could be working on. We're either going to have x and y both be positive, one negative, or both negative. Those are the only 4 options I've got. I can't use a 0 for either x or y. Right there. More questions? We did one that had A and B in it on Wednesday when we were, sorry, on Tuesday when we were talking about models, right? A, P, B minus P, something like that. Here's the simplest version of that. I've just got P minus P squared. Or if you wanted to, you could write it as P times 1 minus P. Please write the separated equation. Just separate it, don't do anything else. Was vergessen Sie hier? What do we have here? Sorry, what do you have here? The German. I've exhausted 90% of my knowledge of German with that sentence. What do we have here? What happens when I separate? I get dt by itself, but the other side is dp over p times 1 minus p. Please don't throw things. I want to integrate. The right side is trivial. Left side is partial fractions. Now, I did deliberately pick something that would be quote unquote easy. And again, I get to say, I know you did this. I also know you didn't like it. I get that. But we should still be able to do it, at least in simple cases. So I say to myself, all right, 1 over p times 1 minus p should be equal to something over p and something else over 1 minus p. And now I do a common denominator on the right. And if the bottoms are the same, then the tops should be the same. But notice on the right-hand side, we have p's, on the left side, we don't. So the coefficients must be the same. Let's regroup this. And I get a minus AP plus BP, which is the same as B minus A times P plus A. And that needs to be equal to 1. What is the coefficient of P on the left? It's coefficient of P over there. How many P's are over there? So that means this must be 0. But the coefficient of 1, the number all alone, is just on the right, the A. So from here, A equals 1. Put that with this, what's B? So that means this can now be rewritten as 1 over P plus 1 over 1 minus P. And I put the dp on the outside instead of on the top. It's okay. And now I can integrate. What's the integral 1 over p?
LNP.
Yay. To do 1 over 1 minus p, I need almost. It's not just ln of p, it's ln of stuff. I need a u sub. U equals 1 minus p, then du is minus dp. So instead of plus ln of 1 minus p, I get minus ln of 1 minus p. And over here on the right, I just get a t. I need to put a plus c somewhere. I'm going to put it on the right because it's easier to mess than trying to mess with it on the left. For the record, if all I want is an implicit equation, done. If I want you to write p equals, we got a lot of algebra to do from here. But again, my properties of logarithms come into play. I'm subtracting. Subtracting becomes dividing. Now I can get rid of the ln with an e. So I have p over 1 minus p equals e to the t plus c. Let's play that same game again. We'll make that e to the t times e to the c, and we'll call that an a. A e to the t. And again, with a little bit more algebra, I can get p alone. It's going to take a lot of work. It's not going to be pretty, but I can do it. I have to cross multiply and then gather all my like terms. It's going to suck. The algebra is there. But that's just algebra, people. That's not calculus at all. That's just algebra. Algebra sucks, but it's doable. I will also say, we have lots of technology. If I have to do a really big partial fractions problem, do I want to do that by hand? 3 cheers for Wolfram Alpha. I'm sure going to say, you're doing this, and it's on an exam that I've done. Seriously, this is not a Calc 2 class. You showed me you knew how to do this once. I don't need to see it again. That many times. Maybe once, twice, but not something crazy. Do it on the computer. I don't want to do this by hand. Which means I could do almost all of this. There's just one problem. I have to ask the same question I asked before. What's my interval? Scroll my way back up to the top. I did something that requires me to be specific. But this equation right here, this is my f of, we called it x and y, but it's really in this case t and p. That's defined everywhere. And its partial derivative with respect to y, p in this case, is also defined everywhere. This is an autonomous differential equation. dy dx is just a function of y. What are we going to have in our picture for our slope field? The stuff you just gave me. When I draw the graph for that differential equation, I draw the slope field. What am I going to see in that slope field? I'm going to see those equilibrium solutions at 0 and at 1. That limits where my solution regions are, doesn't it? I have solutions below 0, solutions between 0 and 1, and solutions bigger than 1. Again, with quite a bit of work. I do end up with this, which is defined almost everywhere because of that key, K at the bottom, the A at the bottom there. If I have an initial value, we can plug it in right here and figure out that value of A. We could also plug it in up there and figure out the value of A. So here's one with an initial value. Let's go to town. I know I need to move the x squared plus 1 from the right side to the left side. What do you want to do with the 4? Move it over or leave it on the right? You can do it either way. Okay, if I do that, then I get dx over x squared plus 1 equals 4 dt. That's separated. Let's integrate. It's the integral of 1 over x squared plus 1. I don't have a 2x to do the u substitution to make that work. I don't have a 2 either. I hate to break it to you. There's no substitution for this one. This is one of the ones that we actually got as a formula last year. You're staring, you're nodding your head, Jack. You remember it?
I remember. This one. Secant? Or
Really close. This one's tangent. But it's not just tangent, it's the inverse tangent. This is the arctangent. But then over here on the right, I get 4t plus c. But now I can fill in the value. What's c? Okay, wait a minute. I got to put the right things in the right places. X of pi over 4. That means this is an x value and this is a t value. So it's the tangent inverse of 1 is 4 times pi over 4 plus c. What's the inverse tangent of 1? What angle has a tangent of 1? Pi over 4. Helps if I subtract in the right direction. C is negative 3 pi over 4. And that means that I have an implicit equation What's my explicit equation? X equals. How do I get x all alone there? I don't have to draw it. What's tangent on the other side? Now, Divine, I actually think it would be useful to draw this to find the interval. Because remember, tangent had lots of asymptotes, right? And in order for me to know what interval this solution works on, I need to make sure it's the interval that contains my initial condition where t is pi over 4. So if I graph this, get rid of all the garbage I was doing earlier, tangent 4x minus 3 pi over 4 graph. Oh, that's not going to help. Let's step back to the standard window. Okay, I see all my asymptotes all over the place, right? Lots of asymptotes here. Regular ordinary tangent. Regular ordinary tangent has asymptotes where? Almost. Right, it's pi over 2 and minus pi over 2. But this is not just regular tangent, this is tangent of 4 something. What does the 4 do? Trig was a long time ago, people. When you multiply inside, you squish the function together. So I squish by 4. So instead of pi over 2, I now have pi over 8. And then I move it over. So I'm going to look at intervals that are pi over 8s. Let me change my window. How about we just go from pi over 2, sorry, negative pi over 2 to pi over 2. And now I can say to myself, oh, the thing I want is pi over 4. Pi over 4 is 0.7. I want that value right there. This is the interval. You need that asymptote, that asymptote. Pi over 2 shrunk to pi over 8 and then moved by 3 pi over 4 divided by 4. So 3 pi over 16. We moved it to the right. So scoot everything over by that much. Finding the interval is the hardest part of this damn thing. I got to remember all this crappy trig stuff. Page 49, example 3 goes through another one with a trig interval as well. Questions? Oh, this one has an initial condition as well. I don't want to do the initial condition to start with. I just want to do the solution. So let's see if we can separate and solve this. Worry about the initial condition in a minute. So if I'm going to separate, I'm going to put the X stuff on the right and the Y stuff on the left. If I factor a Y out on the right, when I do this, I'm going to get 1 over Y dy on the left. But on the right, I'm going to get 1 over x squared, which makes me a little twitchy. So I'll rewrite that as 1 over x squared minus x over x squared. Wait a minute, that's just 1 over x. That means the integration on the right is now power rule and ln's. Nice and easy. The integration on the left is ln's. Nice and easy. Bleh. Oh, wait, there's plus c. Can't forget my plus c. Jalen, using your technique about separating when I do an E, I'm going to get rid of the ln by making an E. So this becomes y, absolute value, is e to the minus 1 over x minus ln of x plus c, which is e to the minus 1 over x times e to the negative ln of x times e to the c. But again, e to the c, that's e to a number, that's just another number. What happens with this piece? Unfortunately, no, I can't cancel until the e and the ln are right next to each other. So what do I do with that minus sign? I treat it like it's a -1, and I bring it in as a power. So the e and the ln become e to the ln x to the -1, and then the e and the ln cancel, and I get 1 over x, because that's what x to the -1 is. This still stays e to the -1 over x. This is just some number. If I get rid of the absolute value of y, that'll make this plus or minus. So I now get y equals plus or minus a 1 over x e to the -1 over x. This is a personal preference. I like putting the exponential at the end. That way I don't have to worry about whether or not the stuff that's in the exponent gets confused with the stuff that's not in the exponent. The e makes a separation. Otherwise, I need parentheses. Makes me less happy. This is because I don't have lines on my paper. So if you write on really small lines and I can't tell what's up and what's down, please make separations like this. Now, something interesting. I can then take this, go back to my initial condition, which was, I'll copy it down from up above, y of -1 equals -1, and I can plug that in and I can get a. I'm not going to at the moment. Just for a second. When we separated, right here in this line, what got eliminated as a possible solution? For both y and x, because I have 1 over y, I have 1 over x, right? Clearly, I can't use x being 0. But notice that if I go back to the not separated version, what happens when you put y equals 0 in there? I get x squared times dy dx is 0. Doesn't y equals 0 work for that? I have a solution that's not part of my one parameter family. We gave those a name. We called those singular solutions. Not equilibrium solutions, but singular solutions. A solution that didn't come out of my one parameter family. In this case, the separation kind of made it artificial. You can't use y equals 0. But if I go back and I look at the beginning, you can use y equals 0. It just won't be a nice solution there. That was the problem with those exceptional points. My initial condition was in there. I might not get a nice way of getting at the solution. That's what happens in this case. Singular solutions come out of these sorts of weird behaviors from setting up our integrals the way we want them to be. Example 4 on page 50 has 2 of those. So please read example 4 to see another reasoning for this behavior. The other thing we said about singular solutions and that nice thing about f of y and partial of f with respect to y was that it guaranteed me a unique solution. It is possible in the process of doing these sorts of things that I could get something that doesn't have unique solutions. That is absolutely separable because I can write it 1 over square root of y dy equals x dx. That's separable. And I know how to solve it. We actually used this one because we came up with the solutions back in chapter 1. This was one where I asked you to verify that we had a solution, and the solution in question was y equals 1/4 x squared plus c quantity squared. Oop. Doesn't help if you can't see it. But notice that if you put y equals 0 into the original equation, it works. That's a singular solution. It's not going to come out of what we get here. There's no way to change that c to make this whole thing equal to 0. But y equals 0 is a possible solution here. But it gets even worse than that. If you graph this equation looks like a kind of fat parabola. It's not quite as curvy. It's kind of squat and a little wider than it should be. If I take the right side of this kind of squat paraboloid, and I take that and I just shift it over a bit, so instead of starting it at 0, I start it at 1. That would be the equation y equals 1/4 parentheses x minus 1 squared plus c quantity squared. For x bigger than 1 and y equals 0 for x less than 1. That's a piecewise defined function. But you know what? That satisfies my differential equation also. The problem is that 0 was that exceptional spot, and now we get a solution that's not unique. So it's possible that you could have more solutions than just the ones you get from actually doing the integral. You could have singular exceptional solutions. You could have non-unique solutions. It is also possible in some really nasty, ugly cases. I just don't know how to do the integral. If I don't know how to do the integral, I can leave it as an integral and say the answer is defined. Y equals this integral. That's okay. But I'm going to try and avoid those. Here's an example of such a problem where when I use the fundamental theorem of calculus, instead of just integrating, I integrate from my initial condition, y of 4, I integrate from 4 to x. Right here. I'm going, well, it's here right now, so it'll be in the recording. I'll scan it, make it part of the notes. But that's the important part, is they get an answer that's defined as an integral. And that's acceptable because we don't know how to integrate e to the x squared. It's just not integrable in any nice way. But this is a technique we did. Chapter 9, section 3. I know you did. I will see you all on Monday. Have a wonderful weekend and try to put your brain back in yours.